helium atom which has a 2 plus sign on top. So that is known as an alpha particle. Again, all this you know from your first PUC. Alpha particles produce light flashes on the screen. So number of alpha particles scattered at different angles can be calculated. So the conclusion of the experiment was that since most of the alpha particles pass through the gold foil directly, we can say that most of the atom is actually empty. Hey all, I'm Hari Krishnan from the Department of Physics, Vidhyaashram PU College, the Temple of Excellence, and we are going to start a new chapter here today, that is atoms. So we learned the special intricacies of dual nature of radiation and matter. Now we are going to jump ahead and learn about the smallest particles we know about, that is the subatomic particles, starting with atom. So, for a long time, people thought that, okay, atom was the smallest particle there existed. That is, the very basic building block of nature was the atom. That was the assumption until it was proven otherwise. So, again, how was it proven otherwise? This particular chapter is very similar to the chapter you already learned in your chemistry classes in your first PUC and in second PUC. That is, we are going to discuss a very simple experiment that is known as the alpha scattering experiment that is done by Rutherford. So again, from the same thing you have studied in first PUC, we are just revising it so that we get an idea of what was the experiment, what was the conclusion, and how this particular progression of the models became or came into effect. Again, we are discussing this in physics because it was physicists who actually found these results and published them, and it was not chemists. So yeah, if anybody asks, physicists are the most brilliant, most topmost people in the world. So again, so what is alpha scattering experiment? So what exactly is an alpha particle? Alpha particle can just be said to be an helium atom which has a 2 plus sign on top. So that is known as an alpha particle. Again, all this you know from your first PUC. We're just going to dive right into the topic, that is the experiment of alpha scattering. So how is alpha particles being scattered? So let's say this is the alpha particle. So when alpha particle was moving in a straight line, it was scattered. So how did this happen? So the experiment Rutherford did was, he took a lead box. He took a box that was made out of lead, and then he kept a source inside which constantly emitted alpha particles through an opening. So there was a source inside which constantly emitted alpha particles like this in one straight beam. So why did he do that? He wanted to find out the properties of the atom. So for that, he did this particular arrangement. That is, he kept an alpha emitter inside a lead box, and then he placed one small piece of gold foil. He placed one very small piece of gold foil that was very thin. So gold is highly malleable, so it can be made to be a few atoms thick. So it is very highly malleable, it is very ductile also. That is why he chose gold foil for this particular experiment. So he kept a gold foil like this, and then he emitted alpha rays at the gold foil. And behind this particular gold foil, he kept a screen that was made out of zinc sulfide. Why zinc sulfide? Because when the alpha particles hit behind the screen, it will produce tiny flashes of light, indicating that, okay, the alpha particle penetrated the gold foil and went behind and hit the screen. And this particular screen is a rotatable screen. So what do you think the experiment results was? Again, you already know what the experimental results were, but still. So again, the results were as expected, that is, most of the alpha particle was scattered and produced flashes of light on the screen that was kept behind, that is, on the zinc sulfide screen kept behind, there was flashes of light. And most of the alpha particles just went through directly without any scattering. And some of the alpha particles scattered at a particular angle, and 1 in 8,000, that is very small number of 0.14% or something, actually came back That is, it rebounded in the initial direction. So this was the thing that was observed from this particular experiment. He kept a lead box. Inside that, he kept a source which emitted alpha particles, and then he placed a zinc screen behind a gold foil so that he can see, okay, what is the result. And most of the screen illuminated with the alpha rays being scattered, and 1 in 8,000 actually returned in the same direction. So why did this happen? What was the nature of the experiment? What were the observations? That is what we are going to discuss in this particular session. So again, the procedure of the experiment is very simple, just what I explained. That is, a radioactive source of alpha particle was kept inside a lead box with a very narrow opening. Through this particular narrow opening, the alpha particles of 5.5 MeV, that is 5.5 mega electron volts of alpha particles, were allowed to incident or strike the very thin gold foil, which had a thickness of 2.1 into 10 raised to minus 7 meters. And when the alpha particles were allowed to collide with the gold foil, it scattered, and this was recorded using a zinc screen which was kept behind this particular arrangement. And when the alpha particles strike the zinc screen, that is zinc sulfide screen, light flashes were produced. So counting these particular light flashes, or determining the positions of these particular light flashes, you can actually determine what is the scattering angle depending on the gold foil and the alpha particles ray of path. And again, alpha particles produce light flashes on the screen. So number of alpha particles scattered at different angles can be calculated. This was the procedure of the experiment that I just explained, known as Rutherford's alpha scattering experiment. And now we have to find out what is the observation of this particular experiment. So what was the observations? The observations were that most of the alpha particles actually went through the gold foil and struck the zinc screen behind the particular gold foil without any hesitation. So, and that is with low or no scattering at all. That is, it deviated slightly or no deviations at all. That was the case of most of the alpha particles. And about 0.14% of the alpha particles actually scattered by an angle of 1 degree. That is, if you get a screen, and if let's imagine that the gold foil was placed like this, then most of the alpha particles went through without any hesitation, and only 0.14% of it actually scattered by an angle of 1 degree. And about 1 in 8,000, that is, when we send 8,000 alpha particles, about 1 in those 8,000 actually deviated for more than an angle of 90 degrees or more. That is, they deflected somewhere around here or here. 1 in 8,000. And very rarely, very few particles, that is, if you're sending a million, about 1 or 2 maybe, that particular particles actually retrace their paths, which means that if they are going in like this, they actually stopped and went back in the same direction. It got deflected by an angle of 180 degrees. 180 degree deflection was noted for a very few fraction of a particle. So this was the observation for the alpha scattering experiment, and now for the conclusion. So the conclusion of the experiment was that since most of the alpha particles pass through the gold foil directly, we can say that most of the atom is actually empty. And since the positive charges was the only thing that can deflect the alpha particle, because the alpha particle itself is positively charged. So since the positive particles are the only factors that can deflect the alpha particle, we say that, okay, all of the positive particles are actually concentrated at the very center. So again, it is concentrated at the very center and it is heavier than the electrons. So that was the second conclusion. And finally, this part, that is where the positive charges are concentrated, this part is known as the nucleus, and the size of the nucleus is very, 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 very small. So again, this was very important discovery, because just before this, everyone assumed that, okay, the atom was in such a way that the positive charges were distributed evenly throughout the atom and electrons were embedded on the atom like raisins in a plum cake, that is known as plum pudding model, or the watermelon model. Like if you cut open a watermelon, the red color will be the positive C of positive charges, or simply positive field that is being laid out, and the electrons will be embedded in that particular positive C, like when you cut open a watermelon. That later came to be known as the watermelon model or the plum pudding model. So this particular experiment disproved that particular model and said that no, the nucleus is present where all of the positive charges are concentrated and most of the atom is empty. So this was actually a groundbreaking discovery. Now we have to learn a new term that is known as impact parameter. So what exactly is impact parameter? Impact parameter can actually be defined as the perpendicular distance of initial velocity vector of the alpha particle from the center of the nucleus. So what does that actually mean? It means that if the alpha particle is going towards the nucleus, so imagine that this is the nucleus. So this is the nucleus indicated by Z times E. Okay, so this is the nucleus, and imagine that an alpha particle is actually rushing towards the nucleus. Okay, so when the alpha particle is rushing towards the nucleus like this, we know that it has a certain amount of velocity to it. So again, if there is velocity, it is a vector quantity, so we can say that this is the velocity vector. So this particular direction indicates that this is the initial velocity vector of the alpha particle. And we know that when it reaches near the nucleus, since this is positive and this is positive, obviously it will ripple away. That is the experiment. But this particular distance, that is this particular distance in between these two, that is initial velocity vector and a line that is drawn from the center of the nucleus, the perpendicular distance between them is known as impact parameter, and it is indicated using the letter B. So what is the importance of impact parameter? That is, if this particular distance decreases, then we can say that the angle of scattering increases, because if this is the distance, then the scattering angle will be more. But if it is moving like this, the scattering angle will be less to none, right? So this particular distance, this perpendicular distance will determine how much the alpha particle is being scattered. So that particular quantity is known as impact parameter, and impact parameter actually determines the amount of scattering or the degree of deflection for the alpha particle. And you have to understand that as impact parameter decreases, the angle of scattering increases, and if impact parameter, that is B, when B is 0, that is during an head-on collision, it just rebounds back at 180 degrees. So with impact parameter, we can actually determine how the alpha particle will behave near a nucleus. What will be the path traced by the alpha particle? So the next thing is distance of closest approach. So what is the distance of closest approach? So imagine that there is a nucleus like this. So there is a nucleus like this, and an alpha particle is going to collide head-on with this particular nucleus. So as it approaches near the nucleus, what happens? Since this is also positive charge and this is also positive charge, due to Coulomb's repulsive forces, this particular alpha particle is starting to get repelled as it gets closer and closer. At one particular point, the entire kinetic energy of this particular alpha particle decreases and fades away, and it gets converted into electrostatic potential energy. But the point is that as it approaches closer, this particular alpha particle slows down and stops at one particular point, and then it rebounds back. So here again, this is happening because impact parameter B is equal to 0. So again, before it rebounds back at 180 degrees, it has a maximum distance at which it can reach near the nucleus. So the maximum distance the alpha particle can reach near the nucleus is known as the distance of closest approach. The closest the alpha particle can come near a nucleus is known as the distance of closest approach. So you can actually define the distance of closest approach as first considering an alpha particle which is moving towards the nucleus with impact parameter B is equal to 0. As it approaches closer, the Ke, that is the kinetic energy of the alpha particle, decreases due to electrostatic forces of repulsion. And at particular distance away from the nucleus, the alpha particle will come to a rest and then rebounds back. So, where the alpha particle comes to a rest, that is the maximum position it can attain near to that particular nucleus. That particular distance is known as distance of closest approach. So again, mathematically we can actually prove or find out what is the distance or what is the formula for calculating the closest distance that alpha particle can approach the nucleus. So again, when it approaches, the kinetic energy is entirely converted into electrostatic potential energy, because at one particular point, for a brief moment, the alpha particle actually slows down and stops. So that is what we are going to calculate as the distance of closest approach. So again, initial kinetic energy, that is initial kinetic energy of the alpha particle can be said to be half mv square, where m is the mass of the alpha particle and v is the initial velocity of the alpha particle. And similarly, the potential energy or electrostatic potential energy we can also calculate, because we know the equation which is K Q1 Q2 divided by R, or simply 1 by 4 pi epsilon naught Q1 Q2 divided by R is the equation for potential energy if there is two static charges. But here we have to take in the case of an alpha particle, so the two charges will be in magnitude equal to the 2 electrons. So again, these two charges are the alpha particles which is going towards the nucleus. So again, in magnitude they will be equal to or can be represented as (2e), because again in magnitude they will be equal to 2 electrons, and then we have to multiply this with Ze, that is the charge on the, or the magnitude of charge on the nucleus, because these are two charges separated by a distance. Here the two charges separated by a distance is the alpha particle which is coming and the nucleus which is kept at a particular distance. So we have to take 2e and Ze. Ze is the nucleus, 2e is the magnitude of the alpha particle, and divided by the distance between them, which is distance of closest approach, d. So using this we have to find what is d. So the only thing we know is that at equilibrium Ke will be equal to U, or simply by conservation of energy, we can say that U will be equal to T. T means kinetic energy, but here we are going to take Ke only. U is equal to Ke, which implies 1 by 4 pi epsilon naught 2e Ze divided by d will be equal to half mv square. Rearranging this, we have an equation for d. So d can be written down as 1 by 4 pi epsilon naught 2e Ze divided by Ke. That is half mv square. Put it downstairs. That is, divide the potential energy you already get by the kinetic energy, and then you will get your distance of closest approach. So the ratio of potential energy to kinetic energy will give you the distance of closest approach. So again, the last thing you need to know about Rutherford's alpha scattering experiment is the conclusions or simply the inferences he arrived at. The model he formed later came to be known as Rutherford's model of atom. So simply what it holds is that it states that the atom may be regarded as a sphere that is having a size of or size in the order of 10 raised to minus 10 meters, and nucleus is actually something which orders in the range of 10 raised to minus 15 meters, and the entire positive charge in that particular atom is concentrated in the center part, where we call it as the nucleus. And most of the mass also is concentrated inside the nucleus only. The remaining mass is distributed as the electrons surrounding the nucleus. So talking about the electrons have no place inside the nucleus. Electrons will be revolving around fixed paths at particular distance away from the nucleus. And this particular revolution, that is, if this is the nucleus, then electrons will be revolving around like this. This is what Rutherford assumed. And the energy or the centripetal force which is required for the revolution is actually provided by the electrostatic forces of attraction between the nucleus and the electron. That is, like this, the centripetal force will be provided. That is, when the electron is trying to move away in this particular direction, the nucleus will pull it towards the center, which means there is an apparent change in the velocity vector. Again, it slips and slips and slips. Just like Earth is going around the sun, the electron will go around the nucleus. So again, this was the assumption made by Rutherford. And finally, the atom as a whole is electrically neutral, which means that how much ever positive charges are inside the nucleus, that will be equal to the number of electrons revolving the nucleus. So charges inside the nucleus, the positive charges inside the nucleus will be equal to the number of electrons outside the nucleus. But this particular assumptions were not actually right. The main problem was that according to the known classical theory, we know that if electrons are accelerating, if any charged particle is accelerating, we already learned also that if a charged particle is accelerating or oscillating, it should produce or emit radiations. So as it accelerates or as it revolves around like this, according to classical theory, this should emit radiation. It should emit radiation in the form of a photon. So if it emits radiation, obviously it will lose its energy. If it loses its energy, it will spiral out of control and then slowly land in the nucleus. So obviously this is not happening. If this was happening, all the atoms will just perish away. So this is not happening. So this was actually a wrong conclusion or inference that he arrived at. This was actually a drawback. And another drawback was that this particular model could not explain the hydrogen structure. That is, the fine structure or atomic spectra of hydrogen could not be explained using this particular model. What is the atomic spectra? What is the fine atomic spectra of hydrogen, fine line spectrum? Everything will be discussed. Don't worry. So for now, know that one of the drawbacks was it could not explain the hydrogen spectrum using this particular model. And again, just to refresh, the electrons were perfectly placed in fixed orbits by Rutherford. Again, we know that that is also not true, because we know that electrons jump from one orbit to the other orbit. In Rutherford's model, it was not allowed. Electrons were perfectly fixed in their respective orbits. So again, this was also a drawback. So assuming that the centripetal force was provided by the nucleus, that is the attraction between the nucleus and the electron, was a drawback. And because of the reason is because if that is the case, then the electrons will radiate energy or radiate radiations and then slowly lose control, spiraling into the center of the nucleus. So that was obviously one more drawback. And giving fixed layers or fixed positions to the electrons to revolve around the nucleus again was a drawback, because later it was proved to be incorrect or incoherent. And then we can say that it could not explain the fine spectra of the hydrogen atom. So that was the drawbacks of Rutherford's atomic model. So again, this was a very small experiment which you already learned in your first PUC in chemistry. I just refreshed it a bit, and then again we'll continue the lesson in another session. I hope you have understood everything I have just explained here today. So until then, thank you.